we've already looked at how to draw Bohr models of the atom, and now we're going to get into how we can abbreviate that, how we can make it so we don't have to draw that every time we need to work with it. So we're going to get into something called the electron configuration. Now, if you go on to take chemistry with me, we will get way more in depth with electron configurations, and they can get really, really ugly. We're going to go with very basic shell configurations, which are just a series of 1 to 4 numbers that kind of describe the address of the electron, or the arrangement of the electrons around the nucleus. But make a note right now to ask me to show you some of the chemistry versions, just so you can see where this builds up to eventually. Anyway, each shell can only hold a limited number of electrons, and I'm going to use the word shell here mostly. However, the word ring also works, the word energy level also works, and occasionally you'll hear orbital. It's got a pickier meaning than that in chemistry, but it's probably good enough for our purposes. And so those terms can be used interchangeably. But we've mentioned this already with drawing Bohr models, that each ring can only hold a limited number of electrons. Now, it's oversimplified here, but the first energy level can hold 1 pair or 2 electrons. The second energy level can hold 4 pairs or 8 electrons. The third energy level roughly does the same. Again, it turns out things get complicated once you get to the 4th row of the periodic table where the transition metals start. But they at least initially hold only 4 pairs of electrons before they move into putting some electrons into the 4th energy level. And it turns out that you put a few into the 4th energy level before we go back and finish filling up the 3rd, because the 3rd can actually hold out to 18 as well. We're just never going to see that this year. Again, if you take chemistry, we do. But we're not going to deal with the transition metals too much this year. And we won't even fill up the 4th energy level in what we do. Anyway, there's this rule in chemistry. It's called the Aufbau principle, but you have to have the innermost ring or innermost energy level filled up before the next energy level can start filling up with electrons. So what that means is that if you're hydrogen, your 1 electron goes in the first energy level, that first ring. If you're helium, you have 2 electrons and they go in that first energy level. Any element after that, their first 2 electrons go into that first energy level, but then the next electrons go into the second energy level, the second ring out. And then we go to the 3rd ring out, but each prior ring has to fill up before the next one can start having the electrons added to it. Anyway, I have here some Bohr models that we drew previously of lithium here, 3 protons and 1, 2, 3 electrons, and chlorine here, 17 protons, and it turns out if you take the time to count, it's 17 electrons. But rather than having to draw one like that over and over and over again, especially one as big as chlorine, where you have to draw the 3 different rings plus the 17 different dots, we can use a shortcut called electron configurations and write it out numerically instead. And so with lithium, normally I would ask you these questions in class, but I'm just going to give you the answers here. So if you look it up on a periodic table, lithium has a total of 3 electrons because it has an atomic number of 3. So that means 3 protons and normally 3 electrons. So then the first orbital, as we said already, can hold 1 pair. Of course, 1 pair would be 2 electrons total. So it can hold 2 electrons. So we put the first 2 in the first energy level, which means we have 1 left to put into the next energy level. And then that becomes our electron configuration. And we read this as dash or hyphen, but 2-1 is the electron configuration of this one. That is that it has 2 electrons in the first energy level and 1 in the next. Now, there are higher energy levels, but we don't write out zeros for all those. It's kind of pointless to write out all those zeros. And so we just say that lithium's electron configuration is 2-1. Every element, helium and above, has 2 for this first number. Hydrogen is the only one that doesn't. Hydrogen has an atomic number 1, so its electron configuration is just 1. Helium is 2. Every element after helium is 2-something. And so on and so forth. So if we skip ahead to chlorine here, chlorine has 17 electrons, has an atomic number of 17, so 17 electrons normally. That first energy level, as we've already said, holds 1 pair of electrons, or 2 electrons total. The next energy level can hold 4 pairs of electrons, or 8 total. And so by the time we put 2 and 8 in now, we've put 10 electrons in, which leaves us with 7 more left. That's not going to fill up the third energy level, so at this point we're ready to write our electron configuration, and it's going to come out to be 2-8-7 for the remainder. And so that is chlorine's electron configuration. You've previously drawn Bohr models of the first 20 elements, and we're actually going to go back to that worksheet and you're going to finish it out, and you're going to start by writing the electron configurations. And it's just taking those Bohr models and writing them out numerically. But you'll get to really quickly where you could just write out an electron configuration without having to draw the Bohr model first. Certainly you're welcome to, but you don't have to. Now, unfortunately, you do need to know these numbers. That the first energy level can hold 1 pair of electrons, that the second energy level can hold 4 pairs of electrons, and so on. You do need to know those numbers. But there is a shortcut. I'm not going to tell it to you here. Ask me in class. Make a note right now. Seriously, write down, make a note. Ask me about the shortcut for electron configurations and remembering those numbers. And I'll gladly walk you through it. I'm not going to give you the answer even in class, but you're going to figure it out, I promise, and you'll do it on your own. Anyway, it turns out that what we really care about in chemistry, what involves, it does most of the reactions and such, is the valence electrons. And most of the mass of the atom, as we said previously, comes from the nucleus, from the protons and neutrons. Most of the space of the atom comes from the electrons and the regions where they occupy. And it turns out that most of how an atom behaves is actually related to those electrons. But it's not even all the electrons, it's just the outermost electrons, the one on that last energy level. And the fancy word for that is valence electrons. So valence electrons is simply the number of electrons in the outermost energy level, or it's the last number in your electron configuration. So you can look back, I'm not going to flip back, but that means that lithium has 1 valence electron, and chlorine has 7 valence electrons. And it turns out there's a pattern on the periodic table that we cover when we cover periodic trends, but everything in the same family, in the same column on the periodic table, has the same number of valence electrons, the same number of electrons in their outermost energy level. It's part of why the periodic table is in the order that it's in, is because of the electron configurations. And as a side note, that's kind of your hint too as to how we'll figure out that pattern, so you don't have to memorize those numbers really. But most of chemistry comes down to just a few electrons on the outermost energy level. But if we go back to when we covered atomic number, I said it's always the number of protons and it's the normal number of electrons. It's not always the electrons, though, because the number of electrons can change. Because it turns out that all atoms want to have a full outer shell, and we call that the octet rule. Now, of course, with an octet rule, you hear oct, octagon, octopus. You hear the number 8. Why 8? Well, it's because the second energy level, the third energy level, and even the higher ones, they always start with 8 in them before we start filling in the extras. So that fourth energy level I said goes out to 18. The third one technically also goes out to 18, but that happens only after those first energy levels have 8 in them. And so the 8 there gives us the octet rule. The first energy level only holds 2. We still call it the octet rule, which is why it's really that all atoms want to have full outer shells, not really that they want to have 8 in their outer shell. Most often, it is 8. And they can do this one of 2 ways. They can gain electrons, fill up that outermost energy level, or they can lose electrons and empty out the outermost energy level. If they empty it out because of that rule that says that the lower energy levels have to be full, then when that energy level goes away, the next energy level down is already filled up, and so now they have a full octet. They have a full outer energy level, which is what all atoms want. And I know I'm personifying the atom there, and they don't really want something, but it's what they do. And they do it because of the way the charges work out between the electron cloud around the atom and the nucleus. So all atoms want, in the end, 8 valence electrons, or a full outer shell, and they can do that by gaining or losing. If you look at the examples we just did, lithium, to fill up that outer shell, it has 1 valence electron. To fill it up, it would have to gain 7. Or, alternatively, it could lose that 1. And which do you think is easier to do? Of course, it's easier to just lose that 1. And so then if it's just losing 1, then its electron configuration becomes 2 instead of 2-1. And it now has a full outer energy level. But now, its number of protons doesn't equal its number of electrons. Lithium has an atomic number of 3, so 3 protons. And lithium then normally has 3 electrons. But if it loses 1, then it has 2. Well, then that means that lithium is going to end up with a charge. And we call charged particles ions, but it's going to end up with a charge, and it has 2 minus and 3 plus, so it's going to end up with a 1 plus charge when we combine those. Conversely, if we look at chlorine, as an example, chlorine has 7 valence electrons, and it has 2 choices. It could lose those 7, or it could gain 1. Which do you think is easier to do? And of course, in this case, it's going to be gain that 1. And so, it's also going to end up with an unequal number of protons and electrons. It's going to have 1 extra electron, and because the electrons are negatively charged, it's going to end up with a 1 minus charge. And so then these atoms are going to end up with charges. And when they have a charge, we call them an ion. So, the general pattern is that metals tend to lose electrons. That's usually because they have less than 4. And nonmetals tend to gain electrons because they tend to have more than 4. To end up with full outer shells, whether that is filling up and completing the current outer shell, or whether that is emptying out and getting rid of the current outer shell so that the lower shells are filled up. It turns out hydrogen is a bit of an exception, and the 4 column is interesting because they have 4 valence electrons, and it's about as easy to gain 4 more as it is to lose 4 more. It turns out, though, it generally follows this metal-nonmetal pattern. So if you look at the column where they all have 4 valence electrons, and you'll figure this out soon which column that is, it's the carbon column. Well, it turns out carbon's a nonmetal, it tends to gain 4. Whereas if you go down that column, you get to lead. Lead is a metal, it has 4, it tends to lose those 4 instead to end up with a full outer shell. And so metals tend to lose and nonmetals tend to gain electrons. And then that ends up giving them a charge, and when they have a charge, we call them an ion. Anyway, that finishes up the notes here, and like I said, you're going to get to practice doing electron configurations and figuring out number of valence electrons, figuring out whether atoms are going to gain or lose electrons, and from there, what charge they end up with because of that. And then that has a huge effect on how reactive chemicals are and what kind of bonds they form, how they bond with one another. And so this valence electron thing and the charges that it causes or that it results in becomes the basis of our next 2 topics after this, the 2 different types of bonding that we see in chemistry. Anyway, be sure if you have any questions that you let me know.